Lesson 11.7 is going to be talking about expanding binomials to powers. Before we go on to that, we're going to review Pascal's triangle. Now, we talked about Pascal's triangle when we were looking at combinations and permutations, more specifically combinations, but technically Pascal's triangle is also a sequence. Remember, it starts with 1 and then has 1 and 1 on either side. This top one is called row 0. This is row 1. Now row 2 is a 1, 1 plus 1 here, middle goes a 2, and then a 1 on the outside. This is technically row 2. Then on the outside again we have another 1, 1 and 2, so in between that is a 3. In between again this 2 and this 1 is a 3, and then a 1 on the outside. That's our row 3. And row 4 has a 1 out here. In between 1 and 3 makes 4. 3 and 3 added up make a 6. 3 and 1 in between them is a 4 and a 1. Technically we could say that there are zeros outside here as well, and that's why right here we have our 0 and 1 make 1. But we don't necessarily need to put in all those zeros. We just know that we start off with those 1s. So Pascal's triangle can be expanded even further into a much larger sequence, which should be in your note packet there, but we're going to move on. So now that we've gone over Pascal's triangle, let's look at what if we needed to expand these binomials to certain powers. Now in lower powers we know how to do that just by distribution or foiling. So if we wanted to expand our x plus y squared, well, we would write it out as x plus y times x plus y, and again we would just kind of foil, so x to x, x to y to x, and y to y, and that would give us something like this, our x squared plus xy plus xy plus y squared. And when we combine those all together, it would give us our x squared plus 2xy plus y squared. We can use that in our next one. If we're looking to expand x plus y to the third power, well, it would look something like this. We would have 3 different x plus y's all being multiplied. But if we just looked at these 2, we know that these 2 are going to be the same as this one here. So we can just kind of quickly say right away that we're using what we had before, this x squared plus 2xy plus y squared times our x plus y. But now we need to distribute everything across. So x squared to x, x squared to y, 2xy to x, 2xy to y, and then y squared to x and y squared to y. So there are going to be 6 different things coming here. It would look something like this. We would have x cubed plus x squared y plus 2xy plus 2xy squared, or 2x squared y plus 2xy squared, plus xy squared plus y cubed. So there's a lot of different terms going on there. Like I said, there are technically 6 different ones, but we can combine a couple of them. We can combine our x squared y's together, and we can combine our xy squareds together. So there should be 3 of each of those. So it would look something like this. Now, instead of going on and continuing to do more, notice how in front of each of these are coefficients. There's a 1 here, 2 here, and a 1 here. In this one, there's 1, 3, 3, and 1. Let's go back and look at our Pascal's triangle. In that first one, we had 1, 2, and 1. And in the second one, there was 1, 3, 3, and 1. So whenever we expand these polynomials to certain powers, they're always going to follow Pascal's triangle, which is going to be very useful when we're looking at how to expand these. So, like I said, noticing from before that when we were going to the power of, we went to the power of 2, we were looking at the second row. And when we were going to a power of 3, we looked at the third row right here. So, looking at using Pascal's triangle, we're not going to be using the binomial theorem per se. We're going to be using Pascal's triangle to solve out these expansions. When we do that, there's a certain directions we should use. The first things is to look at the exponent. The exponent tells you what row to look at. From there, we write down our coefficients. And the coefficients are all of the numbers in the row. And I would also give yourself some space in between each one to write everything else we need. The third step is to look at what's in between them. So here's our term plus, or here's our terms minus each other. If it's plus, everything is positive. If it's minus, then it's every other. Every other. So it would go plus, minus, plus, minus, plus, minus. So you could say every other starting with plus, starting with positive. And I'll show you what that means here in a second. Fourth thing to look at is take your first term, the first term that's in your binomial, and you would go down in exponents from the exponent to 0. So descend or go down from exponent to 0. And the last thing you do is take your second term and go up from 0 to the exponent. And I'll show you exactly what that means here. So in this case, first thing to do, our exponent, what we're going to is 5. So we need to find the 5th row right here. Now that we know our row that we're looking at, we can write down our coefficients. So I'll leave it right there. So we know our coefficients are 1, 5, 10, 10, 5, and 1. So I'd write down 1, 5, 10, 10, 5, and 1, leaving a little bit of space in between each one. So now we're on to our third, which says if it's plus in between, they're all positive. If it's minus in between, then it's every other one. And in ours, we have P plus Q, so we know that they're all going to be positive. So I would say plus 1, plus 5, plus 10, right on down the line here. Oops. Adding each one. Now the last thing we do is look at our first term and go down in powers from exponent to 0. Our first term in this case is P. So after the 1, we would write P to the 5th, P to the 4th, P to the 3rd, P squared, P1, and P to the 0. Then our last thing to do is go with our second term and go up from 0 to the exponent. Our second term is Q. So we start with Q to the 0, Q to the 1, Q to the 2, Q cubed, Q4, and Q5. Now from here, all that's left to do is just simplify things down. So we'd say in this case, if we have positive 1 times P5 times Q to 0, that just leaves us with P to the 5th. In this case, we have plus 5 times P to the 4th, Q to the 1, or just Q, plus 10 P to the 3rd power, Q squared, plus 10 P squared, Q cubed, plus 5P, or P to the 1, times Q to the 4th, plus 1 times P to the 0. We can just kind of neglect those because we don't need 1 or 1. And Q to the 5. So this is our expansion. Instead of having to FOIL things out a million times over, we can just write this full expansion for that binomial. So again, instead of using the binomial theorem, we'll just use the Pascal's triangle to expand one. In this case, we are given a negative. So we'll move this off to the side here, and we'll go right down with our steps. We know that we need row 8. So here's 5, 6, 7, 8. And if you ever get confused about which row you're looking at, it's always the one where the number after 1, that's what you're looking at. So the 8th row goes 1, 8. Or from the right side, it would go 8 and then 1. So now we just need to write down our coefficients, leaving enough space to write in everything else. So 1, 8, 28, we're going to have to write small, 56, 70, 56, probably going to run out of space here, 28, 8, and 1. And I'm going to get rid of this now, so we shouldn't actually need it anymore. Okay, so we know our coefficients. Now from here, the next thing we do is if it's positive, they're all positive. If it's negative, we go every other. It is in fact negative, so we need to go plus, minus, all the way down. Okay, now that we know what we're doing with each one, adding or subtracting, the next thing to look at is taking our first term, which in this case is t. So we'd start t to the 8th, t to the 7th, t6, t5, all the way down, t2, t1, to t to the 0th. Then we take our second term, that s, we go s0, s1, s2, s3, s4, s5, s6, s7, and s8. Kind of looks like a big jumbled mess, but at this point we're ready just to combine everything and solve it down. So if we're looking at our first term, this is our first term or first part of our expanded binomial, it's just going to be t to the 8 minus 8 times t as, or 8 times t to the 7 s plus 28 t to the 6 s squared minus 56 t to the 5 s to the 3rd plus 70 t to the 4 s to the 4 minus 56 t to the 3rd s to the 5th plus 28 t squared s to the 6th minus 8 t s to the 7th and plus s to the 8th. And this would be our total expanded binomial then, alternating plus and minus throughout each one. If we were using the binomial theorem, it would ask us to do a little review on factorials so we know how those work. Remember, this just means 6 times 5 times 4 times 3 times 2 times 1 over 2 factorial is 2 times 1 times 4 factorial is 4 times 3 times 2 times 1. Our 4, 3, 2, 1 and 4, 3, 2, 1 can go away. We'll take 2 out of our 6 and we're just left with 3. So 3 times 5 is 15 over 1, which just becomes 15. That's how factorials work. Nice little review there.